flash it up, the ice builds up, and so then it doesn't shut.
So we were kind of talking about on Monday, I said a December I remembered in history where it wasn't above freezing for the entire month of December. And in fact, they talked about it on the news night before last, right after we'd had that conversation, and it was 1989, because the record cold it was set that during that period, and it was -15.
Huh.
So, yeah, so that was the December I was talking about. It was 1989, and we had cattle in 3 counties, about 1,200 head, and that was, you can talk about frozen waters, and the ice got so thick on the ponds that you literally had to cut a groove from the deeper water in the middle of the pond to the shore, so the cattle could get on the fields that we had just pond water in. So
My roommate got a picture sent to him this morning of cows walking over a lake.
Wow, that's scary.
In Oklahoma, there's a whole herd of them was just walking over the top of this lake.
that is so scary.
No way.
So anyway, yeah, so I just thought I would bring that up. It's one of those things that I was always stuck in my memory is the coldest month I ever remember in my life. This approached that, it just only lasted for a week, right? So just imagine a month of that. Pretty cool. So anyway, quiz next week on Wednesday. And so it'll be over the material we covered. We'll probably finish this chapter up pretty soon and start into the next one. Just to let you know that. And then lab this week, we're gonna do some gasification, make some activated carbon and build a water filter. And then we're gonna use food dye because it's very visual. And we're gonna remove the food dye, or at least lower the amount of food dye with our filter, okay? And then we'll talk about that, and then, you know, depending on the filters you build and those types of things, it doesn't take all of the material out unless you get the very expensive filters like we have on our high purity water system, right, to make very pure laboratory water. But for the most case, if we're trying to make drinking water, that may not be as necessary as to remove most of it, right? And so you have to balance cost benefit, right? How much of the chemical can you allow, but still drink the water without it being harmful to your health? And so you we'll talk about those types of things. Cool? Yeah, so we'll show you how to do that, and you can do it in any place in the world conditions, right? Now the materials that we're going to use. Cool? Yeah. In fact, you'll see some of those in places, third world countries, where clean drinking water is hard to get, and people are now going in and building plants like these to help remove some of those chemicals. Cool? Yeah. So we stopped, I think we were on this slide, and we're talking about sewage and sewage outflow. The next chapter is actually on treatment of waste, okay? And so we'll, in this situation, we're looking at, well, where's the treatment occurring here? If I'm pumping raw sewage out under the thermocline in the ocean, where's the remediation occurring?
The plant.
It's right there. No, right? Well, a treatment plant, but if you dump raw sewage out in the sewage discharge, then it actually happens in nature, right? There's natural mechanisms for that to happen, and in fact, we looked at a stream profile, and if this is raw sewage that's coming out here and we have that sewage plume, then what's the oxygen like in that area?
Wow.
It's very low, right? And what type of fish live there? Trash fish, if that, right? If not just worms and other things that fungi and those types of things that help to break that down. Of course, lots of bacteria. And what about the biological oxygen demand of a situation like that? Is the biological oxygen demand high if I dump raw sewage into the water?
It's going to need oxygen to break down.
It's going to need oxygen to break down. That's why I become anaerobic, because the oxygen is all used up trying to convert that to carbon. Then we have to go to a different set of bacteria, or ones that can operate both as aerobic and anaerobic. And so anyway, so just things to think about when we're looking at larger systems and how that works. Now, I'm going to ask this question: is sewage sludge valuable?
You can spread it on fields as fertilizer.
You can, right? And so it's a resource as fertilizer. We can reuse those chemicals that are there, right? And in fact, with a modern sewage plant, then we can remove most of the carbon and keep the nutrients behind, the phosphorus, nitrogen, and those types of things, and concentrate those into a very, very usable material, right? And you have to be careful, if we have a lot of heavy metals in there, can we also concentrate heavy metals? And then are heavy metals easy to remove from the waste stream or hard? Very hard to remove, okay? So that means that the heavy metals shouldn't go in at all. When we're doing labs in here, we never put a heavy metal down the drain, not intentionally anyway. Does that make sense? Any lab that we're using something that would be detrimental to the environment, such as cadmium, then it would never go down the drain, right? Because of the health risks associated with that and how difficult it is to remove once you get there, okay? So we wouldn't put those down. All right, so Chicago, I don't know what year this was, 3 million tons, it may be more than that now, okay? Potentially contaminated with heavy metals or refractory organics, which are very hard to remove.
So what do they do with all that?
Put on farm fields. Yep. So usually there's spread rules in terms of you can only do a field so often with that, right? So you don't concentrate some of those things that might be bad. Yeah.
I heard it's like 3 years.
3 years, yeah, something along that line.
Okay.
I don't know exactly what it is. I've never used it, and so that's when you usually become familiar, but unless you've read about it somewhere. But that probably is reasonable. I know it's a period of time. Springfield, for example, they there's a spread in the same way in agricultural fields, and they talk about that when we go to tour, that they can only put it on so many per year, and then have to take a time break, and then can put it on again. But it's very valuable in that. Is fertilizer expensive? Anybody fertilized? Is it expensive to put 200-300 pounds of fertilizer per acre on a big farm? Yeah, absolutely. So if you can get it at a much reduced price and get the same benefit, then obviously that's what you would want to do. Other molecules that are in our sewage, soaps, let's talk about those for a little bit. How do I identify a soap?
And it's salt plus the water molecule?
It is sodium with a fatty acid chain. If I just do true soap, then I'm going to put a carbonyl carbon, right? And I'm going to use an abbreviation, right? I don't know how many carbons I made that chain, but that's a fatty chain, and those can vary in length in your soap, okay? And they can also have double bonds in them, right? Be unsaturated or saturated, either one. And on this end is a carboxylate or carboxyl acid if it's in its acid form. But the definition of a soap is a salt of a fatty acid. And so instead of having a hydrogen on this negative charge, as it would as a carboxylic acid, it instead has a sodium salt, for example. So it's a sodium salt of a fatty acid, or a potassium salt would work just the same. Okay? Now, an interesting thing is that this functional group irreversibly, or not irreversibly, but bonds tightly to calcium, for example. So I would get a couple fatty chains on a calcium ion, right? Now, when do I have calcium ions in my water?
When you have hard water?
When I have hard water. So if I have hard water, then those bond to that and make a solid that precipitates, and we call it soap scum. Okay, we've kind of talked about that before. But anyway, and it's actually talked about right here too, right? So soaps derived from vegetable or animal fat, either one. If you watch the movie Fight Club, they use human fat. Nobody know that but me? I'm such a nerd. So, bad movie though. Forms insoluble precipitate with calcium and magnesium. Salt of a weak acid, weak base. Forms that precipitate in the acidic water. And, well, we use soaps for a lot of things, right? Baths, hand washing, those types of things. And so the nice thing about soap is it is biodegradable, okay? And so it's not harmful to the environment. It's a molecule that naturally occurs. And so we can actually move to other molecules called detergents, and some of those are much more stable. We can even have non-ionic or ionic detergents, either one. But alkyl benzene sulfonate was the first one. And so if you use what happens if you use too much soap in a washing machine? You know,
I mean, it bubbles out everywhere.
it makes bubbles, doesn't it? And even like in a dishwasher, if you use the dishwashing soap in place of your detergent, you can get one of those to foam out, right? But now my glass works much cleaner if I put just a little shot of dishwashing soap, right? Just like a dime to quarter size drop. When I get ready to close the door, I just squirt that on the door and then put my detergent in the case. And when I do that, my glassware is always less spotty than when I just use detergent. Okay? So just throwing that out there. It's a little life hack, I guess. So anyway, the nice things about detergents is they don't form the soap scum. Okay? So they don't precipitate with calcium or magnesium. And so in that way, what happens when I get soap scum on things? If it's clothing, it dulls it, right? If it's dishes, it spots them.
And if it's piping over time,
It can build up. But now, do we want some calcium in the pipes?
Yeah.
Yeah, we've talked about that before, right? We want some calcium in there because it puts a protective layer on top of the metal. What happened in Flint, Michigan that was so negative? Was it the water itself, or was it the effect the water had on the pipes? The chemistry of the water on the pipes, it removed that protective layer of the acidity, removed that calcium carbonate on the inside of the pipes, and then it started dissolving the metals, which put trace metals into the water and at high enough concentration that it could cause mental deficit and those types of things. It's crazy, isn't it? How could you let that happen in the modern world, right? Branch chain, ABS, not very degradable. So unlike soap, when it gets into the environment, then it remains detergent, and so it can cause some environmental issues. And so by replacing some of those things with other molecules, better living through chemistry, we can change that chemistry. And so this is showing an ionic detergent with sodium and a sulfonate instead of the carboxylate. So this does not precipitate with the calcium with that sulfonate on there. Cool? Yeah. So detergents. So soap and detergents, we find those. We also mentioned biorefractory organics, all right? And these can include a lot of molecules, benzene, chloroform. Benzene used as a solvent very often. Chloroform has had use in the dry cleaning industry, for example. Styrene and toluene solvents, alcohols, ethers, all of those can end up in the water. They're not, some of them aren't very soluble, but we get trace amounts or very small amounts, but it's just very difficult to get them out because they're very stable molecules. And so in a treatment process, then they just kind of move right on through, okay? And so then they end up in the environment and can cause issues. This is an interesting one. We were talking about ethers, so this is methyl terbutyl ether. I think in this class, have I talked about lead being used for tetraethyl lead being used to increase octane ratings?
Yep.
Right? So that molecule went out of favor, right? And so one of the molecules that replaced that tetraethyl lead is this molecule, okay, MTBE. And so it was put in all the gasoline, right? And when gasoline tanks are leaky and those types of things, then what's happened is this molecule has ended up in groundwater because of that circumstance. So that refractory organic ends up there with some other molecules, maybe the benzene that's in gasoline, because that would be present, xylenes and so on. And so all of those molecules show up in groundwater. And how do you get a refractory organic out of groundwater? Any ideas? Or out of soil? That'd be possible if you would dig it all up, but if it spreads out in a plume and then gets in the groundwater, then it's moving, right? So the only thing you can do is vent it. And so you'll occasionally be around an old gas station and you'll see there's 3 or 4 big fans running with tubes going down into the ground. And so what they're trying to do is push those molecules out of the ground so they don't end up in the groundwater by flushing them with lots of air. So then it puts it in the atmosphere, and in the atmosphere it will degrade faster than it does in, underground without the help of the sun, right? And so there's some studies in the past that have showed levels that are too high even for health tolerances. And so these molecules, well, this is one reason why I want to move away from fossil fuels, right? Even though we're not in a perfect world for the green ones yet, right? But we've got to start somewhere. You guys did see Chevrolet decided to go all electric by 35, right? That's not that far away. You guys realize that? Yeah. So trying to compete with Elon Musk and Tesla, aren't they?
Let's get rid of Chevy for once.
Do I?
So it's time to get rid of Chevy.
I still make the argument, and this is the truth. When I farmed, we drove all Fords, and we had power stroke diesels with the last iteration, and man, those are some amazing engines. And I had a Ford 460 before my first power stroke diesel, which I thought was the most powerful engine until you re-chipped that diesel and you could run off and hide from everybody with pulling a 24-foot trailer loaded with cattle when you have those big hauls going to stockyards, right? And that was the vehicle to have. But then I drove my first Chevrolet, and I wouldn't buy one for a work truck. They really do handle and ride better than my Fords ever did. So that includes 2 Broncos and a.
New Fords are nice. New Fords, I think, ride better than
Do they?
anything else.
Well, I have to try one again because I'm not afraid to switch. So I'm an American car owner. Yes. Now we've owned some Toyotas. My wife has one right now, but I drive American. So does that make sense?
Because our F-350 rides better than our Dodge.
Does it? Well, now my Dodge, I had one Dodge in my life. That was. I actually had 2. That's not true. I bought one, an old elderly man that passed away, and I bought his wife's truck. But that's a whole other story. We'll not get distracted on that rabbit hole. All right. But what I do know is that the materials from combustion engines, right, ends up in drinking water. Okay. And so this is in 1998 a publication which talks about that concern. And finding that's from one of the top environmental journals from the American Chemical Society. And so it's a study looking at that, and there was numerous during that period of time. And so we're moving towards other molecules now, trying to find a safer route that we don't have to drink that. Does that make sense? And so back to the idea that maybe we should look at changing how we power ourselves. All right, and we can talk about Texas today, the move to green energy and the shortage of natural gas has left them without power during the coldest period they've had in years, right? So it's kind of scary. I've got 2 cousins and an aunt that live down there. Luckily, my aunt still has power, and so my cousins were able to take their families and go to her house. So, yeah, but we'll see what happens there. We've talked about these molecules. This is a formal slide on them. We talked about the polychloral biphenyls on when we were talking about Times Beach. These molecules were used in transformers and capacitors, large ones for the big power grid. And so that's a cooling fluid. And so in Times Beach, a contractor thought it would be great to use that to oil the roads to keep the dust down. And these molecules are carcinogenic, and then other molecules that form from them, when it oxidizes and a second bond forms across those, they form the dibenzodioxins and also dibenzofurans, which are also highly toxic, okay? And so anyway, there's a whole bunch of different arrangements, 209 different congeners in terms of the chlorines in that structure, and they're highly stable and able to bioaccumulate. And we talked about that with Rachel Carson, right? And so those structures can cause reproductive problems and cancer. So anyway, cool molecule, right? Very stable, worked really well. but we didn't realize the health consequences from it until after the fact. You guys catch that? Does this happen occasionally? Yeah. Did it happen with some of the pesticides and herbicides that we talked about? Yeah. And so we can't change what we've done in the past, but what do? Change the future, right? And so we take those molecules and we no longer produce them anymore, even though they work great, right, for their purpose, but they cause other issues. Then we move to a new strategy. And will we ultimately hit the perfect strategy? I hope. Okay? Non-toxic, doesn't do any long-term harm, and still effectively does the job of pesticide, right? Does that make sense? Maybe it'll be to just breed things to go eat the bugs that we want to get rid of. I don't know. All right. This is actually a case study looking at PCBs in Puget Sound, and so they found 11.2 micrograms per kilogram, or that'd be parts per billion, right? So dry weight was an order of magnitude below the lowest apparent effects of the threshold of 130 parts per billion. And so this is showing a study that looked at those, and so those remain in the water even though those molecules are never used actually in the sediment. And so how do I get rid of those? How do I get them out of the sediment? I have to dredge it, don't I? So, and in fact, I keep saying I'm going to go look up that PCB in the canal in New York, and I still haven't done it yet, but I'm going to, so that'll end up in this lecture at some point. But anyway, this is in the Hudson River, and the GE factories were along the Hudson River. When they had excess, what did they do with it? Dump it in the river, because pollution is a solution to pollution. And so they did that for decades. And so the PCBs is about 3.5 chlorines per molecule. And aerobic bacteria can actually break those down, guys. I don't know if you know that or not. There are bugs that will eat them, but the anaerobics don't. And so they can take off some chlorines, but they don't get rid of them. And so you have to dredge to get rid of them. That's the way you do it. Who pays for that? GE?
I do.
We do. Okay? Now, GE's still in business, so they're probably footing part of that bill. Okay? So,
When you're
anyway.
saying dredging, are you bringing that to the surface?
You bring that soil up and you pull it out of the river, and you can expose it to air or probably incinerate, those types of things, to clean that up. That's what they did at Times Beach, was they actually put it in an incinerator, incinerated all that soil. So anyway, interesting. This is an area that I worked in graduate school. Okay, so I want to talk a little bit about radioactive elements and their involvement in some of what we're talking about. Now, everybody realizes that radiation naturally occurs. Is that correct?
Yeah.
Right, that we have radioactive molecules, or molecules with radioactive elements in them in our bodies right now, in the air around us, and the materials around us, they're here. Okay, they naturally occur. And so then there's a whole nother set of radioactive isotopes that are non-naturally occurring, and those are the ones I worked with in graduate school. Okay, so we're going to talk about those down on the bottom part of the periodic table. And so, but you have a heavy nucleus, and you can add a neutron to that. It makes an unstable nucleus, and it decays and makes neutrons, and so that is a radioactive process, which is decomposition occurs, right? And you can even do that, add a neutron to a stable nuclei and make it unstable, okay? We'll actually use that for some of the analytical work that I did in graduate school. We took materials, put them into a nuclear reactor, into a neutron beam, and activated the material with excess neutrons. Some of them stuck, made radioactive nuclides, and then we could monitor the decay. And from the decay scheme, we could tell you with very high accuracy what elements were present and what their concentration was. Okay? In fact, it's one of the most effective analytical techniques ever developed. Now, what's the negative? You have radioactive byproducts that you have to deal with, right? So just throwing that out there. Alright, so this is from your book, it's table 12.5, and so it's talking about a couple of the naturally occurring radionuclides, carbon-14, you guys have heard of that one, right? With Valentine's Day so close, right? That's the what? The dating element. So dad joke, but it is the one that it accumulates in atmospheric process. The carbon-14 is incorporated into growing plants, right? So the carbon, for example, in CO2, and that occurs from cosmic reactions. And so anyway, when it ends up incorporated in a growing, well, that amount of carbon-14 remains very, very static in a growing plant, and we can measure that and know what it is based on the composition of the carbon-14 in the atmosphere and then moving into the plant. But then when the plant dies, what happens to the new carbon-14 being put into the plant? It stops, doesn't it? Because it's no longer growing, so it's no longer adding new carbon, and the carbon-14 starts to decay away. And so we can look at the ratio of a living plant to the dead plant material, and then knowing the half-life of the carbon-14, 5,730 years, we can date that material back about 30,000 years. Okay? So when archaeologists are talking about the age of a campfire, then what they can do is collect the organic matter that's remaining in the campfire pit from the wood that was being burned, so there's carbon left, and they can measure the isotopic ratio, carbon-12 to 14, compare that to what it would have been in a living stick, and then predict how old it is.
Yeah,
How did you figure out the half-life?
Because you literally do counts of carbon-14 with a detector, and you literally, it's an experiment where you set that up and you count over a very long period of time, and you know the energy that's being given off, and it's been determined very accurately. Yeah.
What is the carbon-14 decay into?
I'd have to look at that decay
Just
scheme.
carbon-12?
I don't know what that decay is. It doesn't say there, does it?
Okay.
I'd have to go look. It's not on that scheme. So there's a scheme for the carbon decay scheme just like this one.
Oh, yeah.
This is showing uranium-238, okay? And that decays into thorium-234, that decays into protactinium-234, then back to uranium. So it literally becomes the same element twice in this tree, right?
Wow.
Because it's undergoing different types of decay, alpha, beta, and then alpha again. And so in that, then it changes identity in those processes. Now, if you'll notice, some of these processes occur very quickly, 24.1 days, and this is 10 to the 9th years.
It's a long time.
So a billion years, yeah. Cool, you guys with that? Yeah.
The half-life of carbon, isn't that when you get like we think it was this old? That's not a percentage, isn't it? Like
So if I have a pure sample of carbon-14, and I have 1 gram of it, okay? In 5,700 years, I'll have half a gram. And in another 5,700 years, I'll have a quarter of a gram. In another 5,700 years, I'll have 1/8 of a gram. Does that make sense?
right.
And so that's what that half-life is defining, is the amount that half of the material, amount of time half of the material takes to decay into whatever it is. But I don't know what the carbon-14, what it decays into. I don't know if it's alpha, beta, or it's one of those two, but I don't know which one it is. So
It'd be interesting, like, I wonder, like, at what point, like, does, like, say, like, 1% of carbon is carbon-14 now, but 10,000 years ago it might have been 5%.
yeah, but it's much less than that.
Wow.
So, is the abundance on this slide? It's not. I mean, I'll look up the abundance for you, but it's actually, it is so low that, for example, when I'm talking about carbon isotopes and calculating that atomic weight, it's ignored.
Wow.
So we look at carbon-12 and carbon-13. for that atomic weight. And so it's such a small quantity in any given thing that, and in fact, that's why we can only go back 30,000 years, because the signal becomes too weak after 30,000 years to be able to
I see.
measure it. Does that make sense?
Yeah.
Yeah. And so it's all decayed out at that point.
And then if you're gonna go back farther, it'll be just like assuming that the concentration is the same.
We have to start looking, if you wanna go farther back in time, we look at different elements.
Okay.
So potassium, for example, is one that we can look, it has a much longer, half-life, and it's used for actually aging the earth and rock and those types of things.
Is that why it's, carbon dating can be, like, said to be unreliable sometimes?
Yes, absolutely, especially when you get outside that window. So, yeah. So this is the potassium I'm talking about, potassium 40. Right, it naturally occurs, and it has a half-life of 1 billion years. And so it's about 0.0119% of the natural potassium in the body. But it's actually used, that potassium ratio in another isotope is used to age rock that contains potassium. And so knowing or approximating what it was when the rock formed, and then what the ratio has changed to from the naturally occurring source, then they can age rock at the same time. So it's one of the ways they do that. Cool? All right. So I worked in some of these decay schemes when I was in graduate school, and it actually allowed us to do an experiment. This is the particular one that we were working in, but we were looking at materials from Hanford.
Sorry, that's where I'm from.
You're from Hanford, Washington?
Well, no, sorry, north of Coeur d'Alene.
Where at?
Panhandle of Idaho, north of Coeur d'Alene.
Oh, up here?
Yeah, I'm from up there.
So right in here.
Yeah, right there.
Okay, so we work with materials from your home state, or at least surrogates that were made to mimic the sludge waste out there. If you go, I will go and look. How much time have I got? We've got about, I'm going to start this video because we're going to run out of time, so I knew that was the case. But I want you guys to watch this, and then we'll have a conversation about those wastes and the plant and those things next time. So try to keep that in mind. And
Buffering issues anywhere, anytime.